Hello there! In this tutorial you will learn how to create this top-down Zelda style game. And it will teach you all you need to create a more sophisticated game, like using a player camera, creating collisions, and creating the overlapping graphics for a fake 3D effect. In fact, this video is the first part of a much larger video that will create a proper Zelda game. I will upload that one next week, so get subscribed to not miss it. And if you want to see it already, you can find it on my Patreon. Now, before I start coding, a quick setup. Our project consists of two folders, one with code and another with graphics. The code folder already has a few files. I will explain those in just a second. And the graphics folder for now only consists of a folder called test. This one contains one image for the player and another image for the rock. And for now, this is all we need, but for the actual game, this folder is going to become much larger. But with that, we have all that we need to get started. So let's jump into our code. Here we are in the code. And right now I have three different files open. We have main, we have settings, and we have debug. And all three of those are Python files. And if I run the main file, that's the really important one, we are getting this window here. Plain black, doesn't do anything right now, but at the very least we have a window. That is all we are going to need for now. And I guess before we get into the proper code, let's go through this to have a solid basis. Now we are starting all the way up here with importing pygame and sys, that's the usual stuff. The more important stuff comes right below, where we are importing everything from settings. And settings looks like this. We basically have two sections in here. The first one contains the main game variables. Most importantly here, we have width and height of our game window. And those would be flexible. So if the game window is too large for your window, you can make these smaller. I guess you could also make them larger if you wanted to. And then besides that, we have the FPS and the tile size. And I would recommend to keep those two numbers static. Now besides that, we have our world map. And the world map is for now going to be the layout of our game. In this world map, we have our player, that's the P. Then besides that, we have axis, and that is going to be a rock or an obstacle, same thing. And then besides that, we have a ton of empty space, and that is going to be space the player can walk on. So then if I go back to my main file, we have a game class. Let's talk about this in a second. But what we are doing with the class comes down here. We first check if this is our main file, then we are creating an instance of this game class, and then we call the method run of this class. So let's look at our game class. And in here, not much is actually happening. We have our init method, and in here we are initiating pygame, we are creating a display surface, and we are creating a clock. So this is the basic setup you always need for pygame. Then more importantly, we have our run method. And in here, two things essentially happen. The first one is going to be this bit here, and that is going to be our event loop. And right now, we are just checking if we are closing the game. Now, besides that, down here, we are filling the screen with a black color, we are updating the screen, and we are controlling the frame rate. So none of this should be difficult if you have any experience with pygame. However, if you have no idea what any of this means, check out my introduction to pygame. It explains all of this in quite some detail. But alright, so this is going to be our basic setup. Now there's one more file that we have to talk about, and that is debug. And debug isn't actually going to influence our game. Instead, it's, as the name suggests, a debug tool. So it's really just there to give us information about whatever is going on in the game. But it's not actually going to influence the game, so you could ignore it entirely if you don't care about it. And I am going to use it just to illustrate in a bit more detail what's going on in the game. And let me actually demonstrate what it does. So if I go to my main file, in here I can from debug import debug, and then in my game loop I can run debug and print any kind of information that I think is important. So let's say hello, and let's see what we get. Now in the top left of our window, we get the word hello. And obviously right now, not particularly helpful, But later on, this could be a game variable that we want to illustrate. So this is very helpful. All right, but right now I don't want it, so let me get rid of all of that. Now with that, we have our basic setup. Although there's one more thing I would like to add in here. And that is that right now, let me actually demonstrate. In the top left of our window, it says pygame window. And I would rather that this says Zelda or something more customized. And this would be a challenge for you, that I want you guys to change this text to something more custom. In my case, it's going to be Zelda, but you could write whatever you want. All right, let's try it together. Let me close this. And we only really need one line when we are initiating all of pygame. So it happens right here after I create a display surface. And the line we need is pygame, spelled correctly, .display.set_caption. And then here we have to pass in a string. And in my case, it's going to be Zelda. And now if I run this, we can see Zelda in the top left. It really isn't going to make much of a difference, but well, it looks a bit nicer. So with that, we have our basic setup, and now we can talk about the actual level. And our level class is going to become incredibly important. It's essentially the central part of the entire game. So effectively, it's going to be the container that contains all the essential game elements, like the player, all the enemies, the level map, all of the obstacles, and so on. It is really important. And that is actually bringing us to the core concept the level class has to manage. And that is that we have to take all of our sprites for the game, put them in different groups, and somehow manage all of this efficiently. And the key concept to make that work is to use different groups to give different functionality to different sprites. So let me give an example. For a start, we are going to create two groups in our level class. One is called visible sprites, the other is called obstacle sprites. And literally any sprite that is going to be visible will be in the visible sprites class. So this is the only group that we will draw on the screen. At the end of this project, it will contain the player, the map, all the enemies, all the obstacles, and so on. So if a sprite is not inside of this class, it will not be drawn. And for the obstacle group, well, anything that is going to be in here will be able to collide with the player. And anything that isn't in here will not be able to collide. That's fairly straightforward. And how this will become useful later on is that, for example, for our level boundary, so the coastline effectively, I have basically placed sprites there that will interact with the player via collisions, but they are not drawn because they're not in the visible sprites group. You will see how that is going to work later on. But the main thing you should understand is this, that you can put sprites into different groups, and the sprite can be in multiple groups at the same time. And depending on what group it is in, it should be interacting with its environment slightly differently. And that is going to become a key concept to make this entire project work. But let's actually jump into our code and let's implement all of this. So here I'm back in the code, and I want to create a new file. And I will save this one as level.py. And in here, as always, we have to import pygame. Nothing else for now though. And now we have to create a class level. There's no inheritance, but we do need an init method that needs self and nothing else. And I guess now we can go straight to creating the two sprite groups that I just talked about. So let me add a comment here, and let's call this sprite group setup. And in here, I want to create self.visible_sprites. And this is just going to become pygame.sprite.group. And now I can copy all of this. And I want to create obstacle sprites. So these two groups will become really important. And essentially what I want to do later on in my level class is I want to give it another method that I'm going to call run. Doesn't need any argument besides self. And in here, I want to essentially update and draw the game. But for now, I'm just going to add pass because it's not doing anything. And now that I have my level, I can go back to my main. I can import, so from level import level. And what I can do now is create self.level is going to be the level. And then in the game, I can call self.level.run. So we are essentially creating an instance of our level class, this one here, in our main game. And then we are running all of this inside of our loop. So really all we're doing is we are calling this method here. And let me just run all of this to see if it's working. And yeah, it's still looking good. We still can't see anything, but that comes later. So now we have a basic level. Now, next up, there's one more thing I will need in the init method, and that is the display surface. Because at the end of the game, we want to draw all of our game on this self.screen. So we can approach this in two different ways. We could either take this self.screen and pass it in this level. This would be perfectly fine. Although in my case, in my level, let's do it right at the top. We can use a function to just get the display surface from anywhere in our code. And the code for that, let's call this one self.display_surface. All we need is pygame.display.get_surface. And this is going to get us the display surface from anywhere in our code, which is quite handy. As a matter of fact, in the debug method, we are using the very same line if you're interested, but that doesn't matter too much. So now we have our basic level class. It still doesn't do all that much because we're not drawing anything. And to draw something, we essentially have to go through this world.map and draw either a rock wherever there's an X, nothing if there's an empty space, or the player if there's a P. And the problem we have right now is that we neither have an X nor a player. So let's create both of these in a very simple way, and then we're going to cycle through this entire map to place them on the screen. So back in my level, well, actually, this should be a new file. And let me save this one as tile.py. And for now, this is going to be a class that will always going to be a rock. But later on, we are going to make it slightly more flexible, so it can also become a tree or a statue or basically any kind of object. Import pygame as always, that was terrible spelling. And from settings, import everything. And now I want to have a class called tile. And this one is going to be a sprite. So pygame.sprite.sprite for inheritance. That is really important. And now I want to create a dunder init method that needs self. And now this one is going to need a couple of things. Most importantly, we are going to need a position, so we know where to place it. Besides that, I am also going to give it an argument called groups. And this is going to be the sprite group it should be part of. How that is going to work, you see in just a second. But there's a very handy feature to assign a sprite to a group via the arguments. You'll see in a second what I mean. Actually, we can do this right now. So these are the two arguments I need. And the first thing you always need in a sprite, that's very easy to forget, is super.init and then brackets. So we initiate this class here essentially. And what you can do that is super handy is if you pass the groups in here, so the argument we have just declared. Now we are going to need two things. The first one is always self.image and we need self.rect. The two main things you always need for any kind of sprite. And the rect is the easier part. We need self.image.get_rect. And the top left is just going to be the position. So this is the position that we get up here that we will give this tile when we create it. Now for the image, I want to import a file. So pygame.image.load And in here, we first have to get outside of our folder. So right now we are in the code folder. So ... Then we have to go into the graphics folder. And inside of the graphics folder, there's a folder called test. And inside of test, we have a player and a rock. And for this one, I want to use rock.png. And really important, do not forget to convert alpha this rock. With that, we have our basic rock, or well, a basic tile. That's a pretty good start. And I guess what we can also do is let me copy all of this. And now I want to create a new file. And this one is going to become our player. So let me save it as player.py. And now I can paste all of this and change the class name from tile to player. And now, instead of the rock, I want to have the player. And the rest can stay the same. Although this player class later on, we are going to massively change. So there's no point using inheritance between these two classes. With that, we have a player and a tile or rock. So now in our level, we can actually set some basic stuff up. So we can finally actually see something. But first of all, let's see if things are still working, and they do. That's still looking pretty good. And I guess let me really quickly explain what we are going to do. So the really important part in our settings is this world map. And let's go through this thing really quickly just to explain what it is and how it's going to work. So essentially, world map is a list. Here's the start and here's the end. And this list contains a ton of individual lists. And inside of each list, we have one string. That could either be an X, a space, or a P. And this we are going to translate into specific positions. For example, this top left X should have the top left position. So this point here should be position 0 and 0. For the simple reason that it's right in the top left. Now the X right next to it, so this one here, should have the top left position. Let me add a small arrow to make it a bit easier to see. You should have an X position of 64 because our tile size is 64, but then the Y position should still be 0 because it's right at the top. And now for another example, let's say if we want to place the player. I still want to place the top left, and now we have to figure out the X and the Y position. And this could actually be a really good exercise for you. Try to figure out what the coordinates of the player are supposed to be. I know the player is in the column with the index 2. So we have 0, we have 1, and we have 2. So the X position of this point here should be 2 times 64. And let me add X here. And that is going to be 128. And now for the Y position, that's the one we haven't done so far. We can use the lists themselves. So we know this is list number 0, this is list number 1, and this is list number 2. So our player is in the list with index number 2. So for Y, we also have to place the player at 2 times 64, which is still going to be 100. So the top left of the player should be a position 128 and 128. And this sort of logic we are going to do for every single item in this entire list. So I want to go back to my level, and in here, I'm going to create a new method. Let's call it create_map. Doesn't need any arguments besides self. And in here, essentially, I have to nest a couple of for loops. And let me build this up slowly. First of all, I need for row in world_map. And now let's print what we get. So print row. And I guess when we set up the class, we can call this method. So in here, let me add another section and let's call it sprite setup. And what I want to do is self.createMap. So we're just calling this method here. And now if I run all of this, we are getting an error that world map is not defined. For the simple reason that I didn't import the settings. So from settings import star. Now this should be working. There we go. So now we still can't see anything, but now we have printed essentially the entire map that we can see in the settings. So the same map we can see here. Pretty good start, although not particularly helpful. Because there's a really important thing I need to get here. That for each row, I need to know the index, because that is going to be the number I will multiply with the tile size to get the Y position. So besides the row information, I also need to know what index it's on. And this is information I am getting with the enumerate method. So enumerate, and we need row index and row. So now let me copy this. I can print the row index and the row. So now if I run this and close the window, we can see that we have index 0, then the first row, index 1, and then the second row. Or well, the first row, the row of the index 1. Let's put it this way. And this is really important information because this entire row here, I want to multiply for the Y position with 0 times 64, which is going to be 0. But for the second row, or the row of the index 1, we want to go with 1 times 64. So that way, there's always going to be a 64 pixel offset between each row. And all right, now we have our row and our row index. So that is going to give us the Y position. But from that, we also need the X position. So this is going to be another for loop. So let me go back to my settings. Essentially, we went through every single list with this for loop, and we got the list and the index. Now what we want to do is that inside of each of the lists, we want to look at each of these X's and then figure out what the information is, so what's inside of the string, and what index this string is on. And that way, we are going to get our X position. And this is going to look very similar. So for, let's call it call, index, and column, in, enumerate, and now it's going to be the row. And that is literally all we are going to need for the basic setup. So this is going to cycle through every single item, so every single X, empty string, or P inside of this world map. And it's also going to give us the X and the Y position. And I guess just for the formula, now we can get an X and we can get a Y position. The X is going to be the column index multiplied by the tile size. And Y is going to be the row index multiplied by the tile size. And with that, we have converted the world map into a position. So now what we can do is if the column, so each individual item inside of this world map, so X, empty space, or P, and use that information to create a certain kind of sprite. So for example, if column is going to be equal to an X, then we want to create a rock. And for that to work, we obviously have to import the tile for the rock. So from tile, import tile, I think I called it. Yeah, tile. And I guess what we added from player, import player. Essentially, all we want to do is if we have an X, we want to create a tile. And the tile has two arguments we have to figure out. We need a position and the groups. So let me copy them. And the position we already have. That is just going to be a tuple with X and Y. And for the groups, all I want is a list with all the groups this one is supposed to be in. Let's say for now, it's just going to be self.visible sprites. So we can see them, but later on, there are going to be more groups in here. And with that, we have the basic setup. This is not looking bad at all. So first of all, let's run all of this to see if we get an error. And we don't. That's generally a good sign. So now we just have to display this visible sprites and we should be good to go. And I think this could be a good exercise to see if you're still following along. So try to display all the sprites inside of visible sprites. I hope that was a simple exercise, because all we have to do is self.visiblesprites.draw, and then we need the surface we want to draw on, which in our case is self.displaySurface. And now let's see if this is working. And it is indeed working. We can see the top part of our game. We can't see the bottom part, but for that we are going to create a camera later on. But for now, this is looking pretty good. And let me make this a bit smaller. So with that, we have our rocks. Next up, we also want to place the player. So if the column is equal to the letter P, then we want to place the player. So we want to just create the player, and the player is in here. It also has position and groups for now. So let me just copy them in here. And we can actually just copy the arguments from the rock and place them in here. So essentially right now, the tile and the player are identical, but they are going to become very different very soon. But let's try this. And there we can see our player. So with that, we have our basic levels set up. And I guess one more thing that we can do for now is that the tile for the rock should be in two different groups. It should be in the visible sprites, and it should also be, let me copy it, it should also be in the obstacle sprites. I guess let me call it obstacle sprites, not obstacles sprite. That's very annoying to pronounce. Now, you will not be able to see a difference. But now, whenever we create a tile, this tile is going to be in the visible sprites and inside of the obstacle sprites. And later on, this will become incredibly helpful, because essentially what we will do is we will check the obstacle sprites and the player, and if there's any collision, we are going to influence the player from that collision. And this is actually something we could start working on right now. So the next part is going to be about the player. And the player is going to become quite substantial because, well, it's the main player of the game. But for now, we are going to focus on two things only: the movement of the player and the collision mechanics. And that is going to allow us to sort of run around the level already. And I guess let's do all of this straight in the code. That should be the easiest way. Here we are back in the code, and I want to look at my player. And right now, our player really doesn't do all that much. So we have to add a few more things here. Now, first of all, we need some kind of direction the player is supposed to walk in. And this, in my case, is going to be a 2D vector. So self.direction is usually a good name. And what I want is pygame.math.vector2. And don't forget the brackets. If you leave them empty, it's going to be 0 and 0. And this is going to give us a vector that is going to have x and y. And right now, by default, both are going to be 0. And what we want to do is to use keyboard input to change either of these numbers to a certain direction. For example, if we are pressing right, then this 0 for the x should be a 1. And then later on, we are going to multiply this vector with a certain kind of player speed. And that way, this direction would become something, let's say 5 and 0, and our player would move to the right at the speed of 5 pixels per frame. So we essentially have to do two things. Number one, we have to get keyboard input, and number two, we have to multiply this vector by a speed. And well, let's start with the keyboard input. So let's call it just input. Needs self and nothing else, as always. And in here, we need to get our keyboard input. And I guess this could become a good exercise. So try to get the keyboard input for up, down, left, and right on the keyboard, and see if you can figure this out. So first of all, I need to get all the keys that are potentially being pressed. And this happens with pygame.key.get_pressed. And now what I can do is if keys, and we can check for a specific key. Let's say I want to start with pygame.k_. up. And if that is the case, I want to set self.direction.y to -1. And that's all we need. Now we can copy this thing and change this one to down. And now y should be 1. And now we can copy both of them. Although, don't forget, this should be elif. So right now, we are either pressing -1, so our player is going up later on at some point. Now if we're pressing down, this y becomes 1, so our player is moving downwards. However, now we have a problem that, let's say in our game, we pressed down and then we lift up the key again. Our player would keep on moving down because this y being 1 sticks around because we don't change it anymore. And well, our player would just keep on moving downwards, which is not ideal. But we can fix that quite easily by adding an else statement that self.direction is going to be 0. So really all we're checking is the up key being pressed? If that's the case, y is -1. If we are pressing down, y is going to be +1. And if we are pressing neither of these buttons, the player doesn't move in the y direction at all. Actually, I forgot direction.y. And that's it for the y direction. Now I can just copy the entire thing and do the very same logic for right and left. Let's say we want to start with right, and right is going to be x, and it is the positive number. And if we go with k left, this should also be x, and it should be -1, and then direction x is going to be 0. This one doesn't have positive or negative. And all right, with that, we have our basic input. So now we can give this class an update method. So update self, that's horrible spelling. And for now, I just want to get self.input. And now what I want to do back in my level.py, I also want to update all of the visible sprites. So self.visiblesprites.update. And now let's run all of the code and let's see if anything happens. So we can't see anything right now, but something is happening, at least hopefully, inside of our player. And actually, we are able to visualize what's happening by using our debug function. But first of all, back in my level. When I created the player, I also want to put this inside of self.player. Player. And the reason for that is that I'm going to use this self.player quite a bit. And this way I can target it directly. But it is still going to be inside of this visible sprites. And well, now what I can do is right at the top, I can from debug import debug. So this function here. And now in my run method, I can call debug and I can call self.player.direction. And now if we run all of this, we can see in the top left, we have 0 and 0 right now. And that's our direction. And if I press to the left, we get -1 for x, or +1 if I press to the right. And if I press up, we get -1. And if I press down, we get +1 for the y. And that way I can press in the different directions and we get different numbers. So this is already going to give us the keyboard input. And all we want to do is to multiply this with a certain kind of speed. And that is also going to happen inside of the player. So now, besides direction, I also want to give my player self.speed. At least for now, and let's put it at 5. Although be aware later on, this speed is going to disappear because we will replace it with a proper dictionary of all the player attributes. But for now, we can work with it quite well. And besides that, I want to create a move method, and this one needs self, and it's going to need the speed. And in here, we are going to move the player. All we have to do is self.rect. Let's say center plus equal self.direction multiplied by the speed. And that is all we need. So now I can run in the update method self.move, and the speed is going to be self.speed. And let's actually try this and see what happens. So nothing happens if I don't press a button, but if I press to the right or to the left or up and down, our player is moving. So this is working quite well. Although, well, you can see that the overlap with the different rocks doesn't work at all right now, and we have no collisions, but we can at least move around. Obviously, we also don't have a camera, so if the player moves outside the window, it just disappears. But that comes soon. Although before we get to that, there's one more thing I do want to work on, and let me illustrate what the problem is right now. If I just move left or right, or up and down, we have a certain kind of speed. However, if I move to the right and down, we are moving significantly faster. I think it's quite good to see. And the reason for that is trigonometry, essentially, that if we apply two different directions, we are moving slightly faster. And this we have to account for. And essentially what we have to do. In this player, so this direction here, we have to normalize it. And what normalizing means is that we are changing the length of a vector to 1. And that way, if we multiply by the speed, it's always going to have the same speed no matter what direction we are going in. And well, doing that is actually super easy. All we have to do is if self.direction.magnitude, that's how you spell that. So magnitude essentially is the length of the vector. And if that is different from 0, then I want to get my self.direction and simply get self.direction.normalize. So first of all, we are checking if our vector has any kind of length. And as soon as it has a length, we are setting the length of the vector to 1. That way, it doesn't matter which direction it's going in, it's always going to be 1. Which down here in step number 3 is going to result in the same speed in all directions. Now the reason why we need this if statement is because a vector of 0 cannot be normalized. Pygame would throw an error. This is why we need this if statement. But now, if I run main.py, I can move left and right, it still works, but now if I move down, now we can see in the top left we get 0.7, and that is because of the normalization. But, well, you can see in the game, now the movement looks significantly more constant. So that's a pretty good start. And you might have one question, that in the player, why do I add the speed as an argument instead of just writing self.speed? Now, this would work, but the reason why I'm not doing this is later on for the enemies, we want to use the same move method. So what I'm essentially going to do is I'm going to later on remove this move method from the player and put it inside of another class, along with a couple of other methods actually. And then both the player and the enemies are going to inherit from that class. And that way I'm going to keep things a bit more flexible, so both the enemy and the player can inherit from them and use all of these methods. So just keep that in mind if you want to use self.speed. But okay, with that, we have our basic movement. So next up, we have to work on the collision. And collisions generally can be a bit finicky to work with. For the simple reason that in Pygame, all we can really check is if two sprites are overlapping, but Pygame doesn't tell us where they are overlapping. So let me put two sprites on the screen. Right now we have one sprite and one sprite slightly to the right and the bottom. Now these two obviously overlap, but do they overlap from the right or from the bottom? That's a really important thing, because what we want to do if they overlap, we want to place the colliding rectangle either to the right or to the bottom of this other sprite. So the problem we might have is that if we get a collision from the right, Pygame might get confused and place the sprite at the bottom of the other sprite. And in the game, this would look like our players teleporting around, and it might even break the entire game. But fortunately, it can be fixed fairly easily. All we have to do is to apply each direction individually. Let's say we're going to start with the horizontal movement. So we're going to move the player in the horizontal space, check for collisions, and if there is a collision, we are going to move the player to the point of that collision. And once all of that is done, we are going to work on all of the vertical movement and collisions. That way there cannot be a confusion between what kind of collision is going to happen. And well, that is all we need to get started. So let's go back into our code and let's have a look at this. Here we're back in the code and I have my player class open. Now, what I would like is to have all of the collisions inside of this class. The problem is that this player doesn't know where all of these obstacle sprites are. So we have to pass them into the player. And this is going to happen by simply giving the player another argument. And let's call this one the obstacle sprites. And then in the init method, I want to get my self.obstacle sprites. It's just going to be obstacle sprites. And now when we create the player at the end, it is going to get self.obstacle sprites. Be aware here, we are placing the player inside of this group. And then we are giving the player this group here, but just for the collisions. The player itself isn't in that group. That is a really important distinction. All right, with that, we can actually let me create the collision method in here. So let's call it collision. It needs self, and I want to give it a direction. Essentially, what we are going to do. First of all, we're going to check the direction, and this one could either be horizontal, and then we want to do stuff. And I guess let's be a bit specific. So if direction is going to be vertical, then we want to do other collision stuff. And let's work on the horizontal one first. Essentially, what I want to do, I want to look at all of the sprites inside of my obstacle sprites. So for sprite in obstacle sprites, in self.obstacle sprites. And now for all of these sprites, if sprite.rect.collide rect and self.rect. So we are essentially checking the rectangle of the sprite with the rectangle of the player. So this information is going to tell us if there's a collision between these two. But we still don't know if this collision happens on the left or on the right. But this we can also get quite easily because we know the direction of the player. So for example, if this is our player and our player is moving to the right, then it would be pretty unlikely to have a collision on the left side. That would be a little bit strange. Instead, we can kind of predict that we are always going to have a collision on the right side if the player is moving to the right. And then the same thing for the left side. If we're moving left, all of our collisions are going to be on the left as well. I guess important to say here, all of our obstacles are going to be static. So that should make it much easier. All we have to do is if self.direction.x, let's say, is greater than 0. So if that is the case, we are moving right. And if we're moving right, we need self.rect.right. That's not how you spell that. Is going to be sprite.rect.left. So now, essentially what's happening here, if we have our player, so this again is our player is moving to the right. And now our player is colliding with some kind of obstacle and they are overlapping right now. What I essentially want to do is to move the right side of my player, so this side here, to the left side of the obstacle we have been colliding with. So that way it looks like the player is always on this particular side and they're not overlapping. And that is all we have to do with this line here. So now next up, we have to do the very same thing for the other side. So if self.direction.x is smaller than 0, then self.rect.left is going to be sprite.rect.right. So the exact flip side of the other line. This is then all we need for the horizontal collisions. Now, next up, we have to do the very same thing for the vertical ones. And this, I think, could be a really good exercise for you. So after looking at the horizontal collisions, try to do the same thing for the vertical ones. So you want to check for the up and the down movement. Let's try together now, but first of all, I want to add proper comments. So this is moving left. And now let me just copy the entire thing. Now, the first two lines are still perfectly fine. But besides that, I now want to look at direction.y. So if direction.y is greater than 0, we are moving down. And if that is the opposite way, so we are smaller than 0, we are moving up. So if we are moving down, we want to place the bottom of the rectangle at the top of the sprite. So essentially what we are doing, if this is our player again, right now our player is moving down. And if now we are colliding with any kind of obstacle, the bottom of our player should be at the top of the obstacle. So this line here. And then we have to do the same thing for the up movement. So the top of our rectangle is going to be at the bottom of the collision object. And all right, with that, we have our collisions. Actually, not all that bad. So let me minimize this. And now we have to work in this move method. And essentially, we have to take this method here and split it apart into the X and the Y movement. So self.rect.x plus equals self.direction.x multiplied by the speed. And then we can do the same thing for the Y. So if I just left it at this and ignored the collision method entirely, we shouldn't see any kind of difference. And things are still looking pretty identical. Cool, good start. But now what I want to do, after we are moving our player, let's say on the X. After we have done this, I want to call myself .collision, and I want to check my horizontal collisions. And let's just use one of them to see what is happening. So now if I run my main file, I can move to the left and I have proper collisions. Although if I move from the top, nothing's going to happen. And pygame is getting a bit glitchy. But this we can fix quite easily because all we have to do is call self.collision. And now we want the vertical collisions. So now if I run all of this, we get very nice working collisions and everything is working just fine. Cool, this is looking really good. There are no bugs as far as I can see. This is working very nicely. Now the problem is, I can actually demonstrate this. I can move outside of the window, no problem. So this is not ideal. Also, the game doesn't look as good as it could because there are no overlaps. So for example, if I'm on top of a rock, my player stops where the rock begins. But ideally there should be a tiny bit of overlap to give the illusion of depth, which is what we are also going to need. So let's work on these two bits. Now to achieve both of these things, the camera and the overlap, we essentially have to create our own group. Or at the very least, we have to take a sprite group and change some key functionality. And that is very neatly going to bring us into a bit more of an advanced concept inside of pygame. So far, if you followed this channel, we only ever used a group to place a sprite in there, to update them and to draw them. But you can totally take a sprite group and rewrite some core functionality. But to do that, we first have to understand what a group is actually doing. And fortunately, it really isn't all that complicated. Essentially, all that a sprite group really does is that it stores a ton of different sprites. Then it can call the update method in all of these sprites, and it can also draw all of the sprites. And all that is really going to happen inside of a draw method of a group is that we are going to call blit with the sprite and the rectangle of whatever sprite we have inside of that group. So with that knowledge, we can totally override key parts of a group or give it extra functionality. Here I'm back in my code and I want to go to my level and I want to change this visible sprites class to a custom-made group. And let's create that class in the same file. I think that makes sense. And I'm going to call this new class ySortCamera group. And it's going to inherit from pygame.sprite.group. And the naming here has two key parts. Number one, the more obvious one, the camera group. So this sprite group is going to function as a camera. And that's the part we're going to work on in just a second. The other part, the ySort, means that we are going to sort the sprites by their y coordinate. And that way we are going to give them some overlap. Now, in here, we are going to need a couple of different things. First of all, as always, we need a dunder init with self and nothing else. And let me start with a general setup of all the stuff we are going to need. Now, first of all, as always, like with the sprite, we need super, ideally spelled correctly, that tends to help, .init. No arguments are needed. Now, once we have this, we can actually replace our visible sprites with this group. So ySortCamera group. And since we haven't replaced any functionality yet, and we have initiated the original class, this should still work. Let's try it. And we still get the very same functionality. Everything works as intended. So at the very least, we didn't break anything yet. But with this setup, we can make some simplifications. For example, what we could be doing, let me actually go to the display surface and let me copy this line here, just to illustrate what we can do, a very simple example. Now we have our display surface inside of our class. So now I can create a new, let's call it custom draw. And needs self and nothing else for now. And really all we need to create our custom draw is for sprite in self.sprites. And don't forget the brackets. And now we can get all of the sprites. And now all we have to do is self.displaySurface.blit. And we need sprite.image and sprite.rect. So this is essentially what a normal sprite group is going to do. And now in our run method, we can replace our draw from the original group with custom draw. And now we don't need any arguments because we already have the display surface. And let's run this. And it's still working just fine. Except now we're using a custom draw that is going to give us significantly more power. And I guess what I can do, we can get rid of this debug. It isn't useful anymore. Now we want to use this for two specific purposes. Number one, we want a camera. Number two, we want some overlap between the different sprites in the Y direction. And let's start with the camera. That's the more important bit. And the logic to make the camera work is actually surprisingly simple. And all of it happens in the custom draw. That by default, we are always drawing the sprite image in the same position as the sprite rectangle. But we don't have to. We can totally give the sprite rectangle a certain kind of offset. And this is what we are going to use for the camera. So really all that's going to happen in practice, when we are calling blit on the surface, we are still going to keep our sprite.image. But now for the sprite.rect, we are going to add a vector to give them a certain kind of offset. And this vector is essentially going to be our camera, because it's going to give us control where the sprites are going to be drawn. And then really all we have to do is to get the offset from our player and connect this to the sprite rect vector. And once we have that, we are good to go. Essentially, we are going to give the offset of the world to wherever the player is going to be. And well, I think this makes much more sense once we actually implement it. So let's go back into the code. And here we still have our Y sort camera group. And what I want to achieve is that the player is always right in the middle of the window. But that's going to come in just a second. First of all, let me illustrate what I mean with the offset. Essentially, all that's going to happen is we're going to create a vector. Let's call it offset. And this offset is going to be pygame.math.vector2. Needs to be capitalized. And by default, it's going to be 0 and 0. And this vector we are going to add to our sprite rectangle. So all we have to do in here, let me create a new, let's call it the offset rectangle. And this offset rectangle is going to be the sprite.rect.topleft and then plus self.offset. And that way we are going to get a new position. It's not a rectangle anymore, but well, Pygame is happy with a tuple, so this is still fine. So now what we can do is put this offset rect, actually let me call it offset position, that's going to make more sense. So offset position, and now anytime we have any kind of offset, we are going to add this to our rectangle. Now right now this is going to be 0, so we should not be seeing any kind of change. So let's run main.py and we still get the same outcome. But what we are now able to do is if I give this vector some starting positions, let's say 100 and 200. Now if I run all of this, our entire game is slightly offset. So this is the offset we have just given it. So what you can see here is that this distance is 100 and this distance is 200. So essentially, our game itself didn't actually change any kind of position. We are just drawing all of the elements in a different spot. And the distance to that spot is determined by our offset. So this is working really well. Now, next up, what I have to figure out is how to connect this offset to my player. And since I want the player to be exactly in the middle of the screen, I first need half the screen width and half the screen height. And we can do this in the init method. So let's call this half width. And all we need to get this is self.displaySurface.get_size. And for x we need 0. And we want to floor divide this by 2. So we are getting an integer. Now we can do the same thing for the height. And all we have to change is from the tuple we get from getSize, we need the first one. And that's going to be the y one. So now we know how much distance we want from the left and from the top. So all we have to do in our custom draw, I want to get another argument, and that is going to be the player. So when I call custom draw up here, I want to pass in self.player. So now I can access the player and get the player position. And let me add another comment here, and let's call it getting the offset. And in here, I want self.offset.x and then .y. So now we have to figure out these two positions. And unfortunately, we couldn't just add player.rect.center.x and player.rect.center.y. Although it would be nice and simple. Actually, let's try and see what happens if we just use those two numbers. So now back in my main file. Now, if I move the player, we get something, but looks a bit weird. But we do get something. That's at least a start. And essentially, all we have to do is from this number subtract either self.half-width and self.half-height. So now we are getting some kind of weird outcome. And I might be able to see the player. I could see her there for a bit. So now the camera movement is a bit weird. And the reason for that is that this plus here should be a negative. And now let's try this again. It should work. And there we go. This feels significantly better. And with that, we have our offset. And if you're really interested in the math here, I would recommend to go over the geometry a couple of times. It is a little bit weird, but once you go over it, it should make sense. Probably just draw it out a couple of times. Eventually it starts to make sense. But that is literally all we needed for the camera movement. So now we have covered the first part. We have a proper camera movement. So I guess now we can start working on part number 2, the overlap. And this one consists essentially of 2 things. The first one is a hitbox for all of our sprites. So right now, for example, for our player, the hitbox is the entire image. But I don't want that to be the case. I want the hitbox of the player to be slightly smaller than the original image. And these parts are going to be the overlapping parts. But this by itself wouldn't be enough, because our group right now doesn't know what elements to draw on top and what element to draw on the bottom. This is going to be another part we have to make ourselves. It's not actually that difficult, but it's something we have to implement. But I guess let's go through it step by step, and let's first of all start by creating all of our sprites a custom hitbox. So here we are back in the code, and I want to start with the tile. That's going to be the easiest one. And right now we have our rectangle. So this is always going to be the full size of our entire image. I want to give it another attribute, and that is going to be self.hitbox. And the hitbox is going to be essentially the same as self.rect, except now we want to change the size. And this happens with inflate. And what inflate essentially does is it takes a rectangle and it changes the size. So in my case, really all I want to do is if this is my original rectangle, then I want the hitbox to look something like this. So we have the same width, the same center, but the top and the bottom are a bit shorter. And that way, later on, the player could be standing behind this, for example. And that's really the entire idea of all of this. And inflate needs 2 arguments, one for x and one for y. Now my x can just remain 0. But for my y, I want to have a specific number. And let's say, just to get started, let's go with -10. Oh, and by the way, this is going to keep the center point at the same position. So let me draw all of this again. This is our original rectangle. And now our hitbox is going to have the same center, but now on the top and the bottom, we are going to have a 5 pixel because we specified -10 up here. And -10 makes the entire thing shrink by 5 pixels on each side. And now we have to do the very same thing for the player. And let me do it right below the rectangle. So self.hitbox is going to be self.rect.inflate. And for my player, let's say for now, I want to go with 0. And since the player is a little bit taller, I want to go with -26. And now let's run the code. And well, this shouldn't make any difference for now, but at least the code isn't crashing, so that's a good start. But now, essentially what I want to do, I am not going to move the rectangle anymore. Instead, I'm going to move the hitbox. And I'm going to move the hitbox and check collisions on that hitbox as well. And after all of that is done, I'm going to put the center of the rectangle where the hitbox is going to be. So that way, the rectangle always follows the hitbox. And that way, I can get all the collisions with the hitbox and have some overlaps, but then draw the player in the correct position. So essentially, what we have to do. Let's go with move first. And let's get rid of this comment. We don't need that one anymore. So instead of self.rect.x, we want to move self.hitbox. and we want to move both X and Y. And at the end of all of this, we want to get self.rect.center is going to be self.hitbox.center. And now what we can do, that instead of checking the rectangle of all of the sprites, we want to check the hitbox. So this should be hitbox. And we're also not going to check the rectangle of our player, but the hitbox of our player. And this is going to happen for basically all of the rectangles. We're going to replace them with the hitbox. So this should be hitbox, this should be hitbox, this should be hitbox, 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 and finally hitbox. And now let's see if this is going to work. So now we can indeed see some offset. So right now our player is behind the rocks, and this is looking really, really good. The problem we have now is that our player is always below the rocks. So no matter where we go, or except here, because these rocks were created earlier in the level setup. So these rocks are behind the player because they were created earlier in the code. But these were created after, these were created after, and further down here, all of these rocks are above our player. So this is going to look kind of silly, but we are very nearly there. So we are making some definite progress. There's only one more thing that we need. So right now we have a custom hitbox for both our player and for our tiles. Now the last thing we have to do in our Y-Sort camera group, we have to order our sprites. So we have to tell it when to draw each of these sprites. And right now they are being ordered by the time of when they are being created. This happens here. Some of the tiles were created before the player, but some tiles were created after the player was created. So those tiles would be on top of the player, whereas the tiles created before the player was created, they would be below the player. And in most situations, this really doesn't matter. But in our case, we don't want to order our sprites by that logic. Instead, we want to order our sprites by the Y position. And essentially the sprite that should be drawn on top should be the one with the highest Y position. Because if the sprite is a lower Y position than another sprite, then the sprite that should be behind or high up on the screen should be behind that other sprite. In Godot, for example, this is just being called Y-Sort. And this is basically what we're implementing ourselves manually right now. And the way we are doing it is by using the sorted function. And let's do this straight in the code. So here right now, we are just going through all of the sprites. But this I don't want to do anymore. Instead, I want to go with for sprite in sorted. And sorted essentially takes two arguments. First of all, it wants a list of what we want to sort. And this we do have. It's just self.sprites. And again, don't forget the brackets. It's very easy to do. And next up, it wants some kind of key. And the key is essentially going to be by what kind of metric we are going to sort all of the sprites. Now in our case, this should be the Y position of each of the sprites. And to get that, we basically need a lambda function. So lambda, and I want to look at this sprite. And all I want to return is sprite.rect.centerY. I guess let me know if you want a specific video on the sorted function. Once you understand lambdas, it's actually pretty simple. But now we have overlaps. So let me run the code again. And now we are still behind the rocks. But now if I go a bit further down, now we are on top of the rocks. But if we go behind them, we are, well, behind them. And all of our collisions still work just fine. And all of the overlapping works really nicely. And this is going to make our game look really good. So cool. This is working exceptionally well. Nice. There are no bugs or anything. This is all working good. Cool. And with that, we have a basic top-down game with a camera, collisions, overlaps, and all of the good stuff.